In the previous presentation, we had discussion on the important points about the capacitor. Now, in this presentation, we will be talking about the energy stored by the capacitor. Now, as we know that the capacitor stores energy in its electrical field. And we also know that the current through the capacitor is equals to C dV divided by dt. And we also know that the electric power is equals to I into V. So putting C dV divided by dt in place of I, so we get power is equals to C dV divided by dt into V. Now, as we know that the power is also equals to the rate of energy, Now, to find out the energy from this equation, multiplies dt on both the sides, so we get du equals to P into dt. Now, to remove this derivative, we can take integration on both the sides, and the limits of this integration is from 0 to e. So the integration will cancel derivative, so the resulting energy will be equals to the limits from 0 to v, P into dt. Now, to understand these limits, let's take an example in which we have a parallel plate capacitor which is connected across the terminals of a DC voltage source. So initially, when the switch is open, there is no net positive and negative charge stored on the plates of this capacitor. So there is no potential difference across the plates of this capacitor. So initially, the potential difference is equals to 0. Let's say Vi. And when the switch is closed, so the positive terminal of this DC voltage source will attract electron from the upper terminal, and the lower terminal will repel electrons towards the bottom terminal. So as a result, the net positive and negative charges will be established on the plates of this capacitor. This process will go on until the potential difference across the plates of this capacitor is equals to the potential difference of this DC voltage source. So we can take the final voltage or the potential difference across the terminals of this plates is equals to the potential across the terminals of this DC voltage source. So we can take the limits from 0 to V. Now, as we know that the power equation is equals to C dV divided by dt into V. So putting this equation here in this equation, so we get energy is equals to from 0 to V. So instead of P, we can write down C dV divided by dt into V dt. So dt will cancel dt, so we get the energy is equals to from 0 to V, C dV into V. So we can rearrange this equation in the form the energy is equals to C, in this case is a capacitance of a capacitor which is constant. So we can write C outside, from outside these limits are from this integration. So we get 0 to V into dV. Now by applying the integration, so we get C V square divided by 2, and the limits are from 0 to V. Now applying the limits, so we get V square divided by 2. So the energy stored by a capacitor is equals to 1 over 2 CV in square. So this equation represents the amount of energy which is stored by a capacitor. So from this equation, we concluded that the energy stored by a capacitor is dependent only on the magnitude of voltage across the terminals of this capacitor, not on the manner of reaching that magnitude. So it's all for today's presentation. If you have any doubt, ask in the comment section. See you in the next one.